In lesson 4 and 5, we proved arithmetic geometric mean inequality for 2 and 3 numbers. In this lesson, we prove arithmetic mean of n positive real numbers is greater or equal than their geometric mean, and equality holds when all of them are the same. Let's call this statement Pn. To prove Pn, we use mathematical induction. It's a very unique way of using mathematical induction done by Cauchy. He proved the base of the induction, then he assumed if Pn is true, then P2n is true. In the third step, he proved if Pn is true, then Pn minus 1 is true. For base, we already proved it. The second step is assuming arithmetic geometric inequality holds for n numbers and prove them for 2n numbers. This means a1 plus a2 plus a2n is greater or equal than 2n times 2nth root of a1, a2, a2n. This is what we want to prove, and we know arithmetic geometric mean inequality for n numbers. a1 plus a2 plus a2n can be written as a1 plus a2 plus an plus 1 plus an plus 2 plus a2n. Each of this is greater or equal than their geometric mean. This means the addition of the first n term is greater or equal than n times nth root of their multiplication, and also for the last n terms. Now if we use arithmetic geometric mean inequality for these two terms, we have a1 plus a2 plus a2n is greater or equal than square root of n2 times nth root of a1, a2, an times the square root of an plus 1 to a2n, which is what we wanted to prove. Now we assume Pn is valid, and we prove arithmetic geometric inequality holds for n minus 1. So we know a1 plus a2 plus an divided by n is greater or equal than a1, a2, an nth root. Let's assume an is n minus 1 root of a1, a2 to an minus 1. Therefore, a1 plus a2 plus an divided by n is greater or equal than nth root of a1, a2 times an minus 1, n minus 1th root of a1, a2, an minus 1. We know nth root of x times n minus 1 root of x is the same as, if we take the common denominator between one and 1 over n minus 1, we have n over n minus 1 And this gives us nth minus 1 times a1, a2 to an minus 1, which is an. As a result, a1 plus a2 plus an over n is greater or equal than an. We times both sides by n, and bring an to the left side, and this means a1 plus a2 plus an minus 1 over n minus 1 is greater or equal than an, which is n minus 1 root of a1, a2, an minus 1. Let's recap. Pn is true for 2 and 3. If Pn is true for n, it is true for 2n. And if it is true for Pn, then it is true for Pn minus 1. Let's see how have some feeling about the proof. It is true for 2, therefore it is true for 4, 8, 16, and so on. Because we already proved it is true for 2. Since it is true for 4, it is true for 3. And since it is true for 8, it is true for 7. That means it is true for 6 and 5, and therefore it is true for all natural numbers based on induction. Thank you.